Dear students, so today we'll discuss chapter number 6 from module 2, that is process synchronization. So this is my first lecture on this chapter. So these are the contents that we are going to discuss from this chapter. So we'll start the discussion with background. So that the critical section problem, Peterson Solution, Synchronization Hardware, semaphores, classic problems of synchronization, and monitors. The objectives of this chapter are to introduce the critical section problem whose solutions can be used to ensure the consistency of shared data. Second, to present both software and hardware solutions of the critical section problem. Third, to introduce the concept of an atomic transaction and describe mechanisms to ensure atomicity. So let us start the discussion with the background study. So we know that the modern computer systems are the multiprocessing systems, and we know that the number of processes will be accessing the resources that are shared among all. So in this case, maintaining consistency is very important. That is data consistency. Means it should not happen like one process is modifying the content of the shared file or a shared data, and at the same time if the other process accesses the same data block which the first process is changing, so the result is the second process, although it want to just read the content, it will not get the appropriate data. So that's why when you share the resources among the number of processes or the users, so maintaining consistency is very important, and this is achieved through synchronization. So that is what we are discussing here. Okay. So the concurrent access to the shared data may result in the data inconsistency. Maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating processes. Very important thing. Okay. We saw that when the common shared data is accessed by the number of processes, so there is a possibility that the data inconsistency problem may arise. So in order to avoid this, so there is a need of mechanisms through which you can impose an orderly execution of cooperating processes. Means you can set an order, and in that order only the cooperating processes should execute in order to maintain the data consistency. Suppose that we wanted to provide a solution to the consumer producer problem that fills all the buffers. So I think you are aware of the consumer producer problem. So the consumer producer problem means here we have the two processes. One process is consumer, another one is producer. As the name itself indicates, consumer means it will be consuming the data that is produced by the another process, that is producer. So here, in order to generate the data, the producer will be having some buffers. So in that buffers it will be placing the data, and consumer process, whenever it want to consume the data, it will be consuming the data from those particular buffers. So it's a classic problem. So through this problem only we'll try to understand the concept of synchronization and maintaining data consistency in this chapter. So here suppose that we wanted to provide a solution to the consumer producer problem that fills all the buffers. So what is to be done to provide a solution for this problem? So we can do so by having an integer count that keeps track of the number of full buffers. So one option is you can use an integer variable count, okay, and the value of this count will be incremented each time whenever a buffer gets full. Okay, at the same time this is for the producer, because producer it is going to generate the data and it will be putting that data into the buffer. So whenever one buffer gets full, so you can increment the value of this variable count. At the same time, the consumer process will be consuming the data from the buffers, and whenever it consumes the data of a particular buffer, when that buffer becomes empty, you have to decrement the count value by 1. Okay, so this should be continuously done, and initially the count is set to 0 to indicate presently initially, so no data is available on the buffers. So this is one possible solution. So it is incremented by the producer after it produces a new buffer, and is decremented by the consumer after it consumes a buffer. So that's what we discussed. So let us see how this can be implemented here. So I think in my one of the previous lecture also we have discussed about this producer and consumer problem, and we saw that there are two variables, that is in and out, through which it is possible to know where exactly the free memory is available and where exactly the full data block is available. Okay, the free memory is used by the producer to place the data that it has created. Okay, and usually that is indicated by in. Okay, so what is in indicates the next free memory available where the data can be put by the producer. Similarly, the consumer will be interested in the memory location where the data is full. Okay, so that it can perform the read or the consume operation. So that is denoted by the pointer out. Okay, so the producer uses the pointer in and consumer uses the pointer out. Okay, so here we'll see how exactly this producer process can be implemented. So we have the while loop here. So while count is equal to buffer size. So what is this variable count? Count we have taken to indicate the number of full buffers. Okay, and here we have defined a constant, that is buffer size, that indicates the maximum size of the buffer. So each time whenever you add a block of data, the count will be incremented by 1, and when count is equal to buffer size, that indicates your buffer is full. Your buffer is full means there is no free space to add a new data. So that's why when the buffer is full, when there is no free space to add a new data, how come the producer can produce a data and it can place where it should place? So that's why when count is equal to buffer size means when the buffer is full, it will not do nothing. It will not do anything. Okay, so that's why it is shown by the empty statement, that is semicolon. Okay, do nothing until count is equal to buffer size. It's a while loop. So when this condition becomes false, then only the remaining lines will be executed here. So when this condition becomes false means when count is not equal to buffer size. Okay, means there is a free space on the buffer. So in that case, what the producer should do, it should produce the data and it should place that data onto the buffer. Okay, so for that we have these lines, that is add an item to the buffer. So to add an item to the buffer, you use the pointer in. So buffer of in will give you the next free space available on the buffer. Okay, so buffer of in equal to item. So the newly created item will be placed in on the buffer at position in. So once you occupy this memory block that is pointed by in, so you should point to the next free memory block. So for that we increment the value of in pointer by 1. So it is in equal to in plus 1 mod buffer size. Why mod buffer size? Because the value of in should not exceed this buffer size. It should be in the buffer size only, and we will be using a circular array for this buffer. So that's why we have to use mod buffer size here. Okay, so here as a result you have added one block of data to the buffer. Again to indicate this, we have to increment the count value also by 1. So it is plus count. Okay, so this is how you can implement the producer process. So next we'll see how to implement the consumer process. So as I told you, the consumer is a process which will consume the data that is produced by the producer and which is placed in the buffer. Okay, so that's why whenever you want to consume a data, so first you have to check whether is there any data in the buffer or not. So for that, first it will check whether the buffer is empty. And to check whether the buffer is empty, the condition is count equal to 0. Because we have used a variable count to indicate how many blocks of data or how many buffers of data are full. Okay, so here initially count will be equal to 0 whenever a producer produces the data, and when it places a block into the buffer, the count will be incremented by 1. At the same time, whenever the consumer process consumes the data, the count will be decremented by 1. Okay, so here at the beginning we'll check whether the count is equal to 0. If count equal to 0 means the buffer is empty, so we don't have any data for consuming. So that's why the consumer process cannot do anything if the data is not available. So that's why here, while count is equal to 0, we have empty statement, okay, which indicates the buffer is empty. So this will be continued until there is a data on the buffer, and when there is a data on the buffer, we know that the count will be incremented by 1, and obviously it will not be equal to 0. So in that case only the remaining lines will be executed. Okay, so here in the following lines what we have to do, so we have to remove an item from the buffer, and that is to be consumed. So for that, first we have to take off an item from the buffer, and we know that the pointer out is used to indicate the next full data block which is ready for the reading or the consuming. So here we write item equal to buffer of out, means the data block which is pointed by the pointer out will of this buffer will be taken, and this will be stored into the variable item. So once you consume the data block that is pointed by this out, again out is to be incremented by 1 for the next filled block. So that's why we write out equal to out plus 1 mod buffer size, and after that, as we have consumed one block of data, so you have to decrement the count value by 1, so it is minus minus count. So in this way the consumer problem can also be implemented. So next we'll see how exactly this the use of count variable is implemented through the registers on the system. So the count plus instruction can be implemented like this. So you take one register, that is register 1. So first you have to load this register 1 with the value of count. Okay, so once you load the value of count into the register 1, you have to increment the value of register by 1. So it is register 1 equal to register 1 plus 1. Okay, so once you increment the value of that is present in the register 1, again you can store back that value to the count. So for that we have written count equal to register 1. So this is how the count plus can be implemented. Very simple. Similarly, count minus can be implemented like this. So for this we use one more register, that is register 2, which is loaded with the count value initially. So after that we have to decrement the count value by 1 because it is minus. The count value is present in register 2. So we decrement the register 2 by 1, that is register 2 minus 1. The new value is stored in register 2, and after that the new value is assigned to the variable count. Okay, so we'll consider one scenario. So how exactly these two lines will be executed, that is count plus and count minus. So consider this execution interleaving with the count equal to 5 initially. So initially let us consider the value of count is equal to 5. So at time t0, let us consider the producer executes this first line, that is register 1 equal to count. Okay, so register 1 equal to count means the count value will be loaded into register 1. So count is 5, so 5 will be loaded into register 1. So as a result, the value of register 1 will become 5. Okay, so after some time at time t1, so let us consider the same process, that is producer process execute register 1 equal to register 1 plus 1, the next iteration, register 1 equal to register 1 plus 1. So the value of register 1 will be incremented by 1. So the register 1 was 5 plus 1, this register 1 will become 6. Okay. So after this at time t2, let us consider the consumer starts execution, and consumer will execute the first instruction from its state. So it is register 2 equal to count. So register 2 equal to count means what is the latest value of count? Count is 5 only, you have not yet changed the value of that. So the 5 will be loaded into register 2. So register 2 will become 5 now. Okay. So let us consider at time t3, consumer will execute the next instruction of its set, that is register 2 equal to register 2 minus 1. So you have to decrement one value, the value of count by 1. So register 2 is already holding 5. So 5 minus 1 it will become 4. So as a result, the register will hold the value, register 2 will hold the value 4. So after this, let us consider at time t4, the producer execute the last line of its set, that is count equal to register 1. Okay, so count equal to register 1 means what happens here? What is the content of register 1? Register 1 content is 6. So the 6 will be added, assigned to count. So count will become 6. Okay. So after this again, let us consider a time t5. The second process will also, that is the consumer will also execute its last instruction from the set, that is count equal to register 2. So when count equal to register 2 is executed, the value of register 2 is 4. So as a result, the 4 will be assigned to count. So count is equal to 4. So in this way, when the two processes are allowed to execute parallelly, the result is inconsistent. Why? Because here we know that the count value was initially 5. So producer what he had, it will increment the value by 1. Count plus plus means, count plus plus means what it indicates, it has produced one data block. Okay, so that is available. So count will become 6. Okay, so at the same time, when the producer, consumer executes count minus minus, that indicates the consumer have consumed one block of data. So the producer have produced one block of data and consumer have consumed one block of data. Means whatever the data block that is produced by the producer, that is consumed by the consumer. So as a result, we expect the count value to remain same as 5. But here, if you execute in this way, the count value is 4. The latest value of count is 4, which is not correct. Okay, so this indicates, so whatever the situation that is created here, so this itself is called as the race condition. Okay, so next we'll see, we are going to discuss all these things again in detail. We'll see the solutions for this also, but before that we'll discuss one more problem. It is critical section problem. So what is this critical section problem? So let us consider there are n processes denoted by p0 to pn minus 1, and each process will be having a segment of code that is called as a critical section. Okay, so what is this critical section? So this is the section of code where the process will be modifying the common variables, updating a table, writing a file, and so on. The best example is whatever the discussion we had in the previous slide, that is count variable. So you know that the count variable is shared among both the processes, that is producer and consumer. So that's why here we expect that whatever the lines that modify the value of count, so it should be placed in the critical section. Okay, so that we'll see in the next slide again in detail. So you just remember what is critical section. So critical section is a segment of the code of a particular process where the process will be modifying the values of the shared variables or the common variables. Okay, so the critical section problem is to design a protocol that the processes can use to cooperate. Each process must request permission to enter its critical, very important. So that's what I told you. Whenever a process want to enter a critical section, first it should send a request for the permission. Once it has the permission, then only it can enter its critical section. So this by this critical section, as a process which is having the critical section, the structure of such process can be shown here. So we have a while true infinite loop, and here in this we have the entry section where the process will be seeking a permission to enter the critical section. So once the permission is granted, it will enter the critical section. It will execute the lines of code that are part of the critical section, and once it completes the execution of all the lines, it will go for the exit section, so which will exit from the critical section, and after that it is having the execution of the remainder section. So this is about the critical section problem. So next we'll see the different solutions for this problem. Okay, so before we start the discussion of solutions to the critical section problem, so first we'll discuss the requirements for the solutions to the critical section problem. Means once you develop a solution to the critical section problem, so that critical section solution should have these three properties or three requirements. So what are these three requirements for the solution? The first one is mutual exclusion, second one is progress, and third one is bounded width. So the first one is mutual exclusion. The mutual exclusion means what? If process Pi is executing in its critical section, then no other processes can be executing in their critical section. Means at a time only one process will be allowed to execute in critical section. Okay, when process Pi is executing in its critical section, so no other process should be allowed to execute in their critical section. Okay, this is first one. The second requirement is progress. Means if no process is executing in its critical section and there exist some processes that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. Means what here? If presently no process is executing in its critical section and if there are some processes that are waiting to enter the critical section, the request should be granted immediately for one of the process. It should not be postponed indefinitely. When unnecessarily the processes should not wait to enter the critical section if there is no any process that is presently executing in the critical section. So this is the second requirement. Okay. So the third requirement is bounded waiting. Means here there should be a particular bound on the number of times the other processes are allowed to enter the critical section. After a process has made a request to enter its critical section and before that request is granted. Means here whenever a process want to enter the critical section, so some processes may enter the critical section so frequently. So that's why in order to restrict or control this one, so you have to maintain a bound on the number of times a process will be allowed to enter a critical section whenever you are granting a request of the other process to enter the critical section. So these are the three requirements for the solutions that you want to provide for the critical section problem. So we'll discuss the first solution, that is Peterson solution. This is a software solution for the critical section problem. So this is also called as popularly two process solution because we have the two process here. So for this Peterson solution, it uses the two variables. Means here we expect that the two processes share these two variables, turn and flag. Okay, so here int turn and boolean flag of 2. Okay, so turn indicates a process, indicates whose turn it is to enter the critical section. Means if let us consider turn equal to the value of turn is equal to I, that indicates process Pi is ready to enter its critical section. Okay, means here if the variable turn indicates whose turn is to enter its critical section and flag of 2. So here the flag array is used to indicate if a process is ready to enter the critical section. If flag of I is equal to true, that implies Pi is ready to execute, and turn equal to it is the turn the turn of a process Pi to enter the critical section. So here these are the two variables that will be shared between the two processes. Okay, in the Peterson solution. So in this Peterson solution, the algorithm for process Pi will go like this. So we have the infinite loop here, that is while true. In this we have a do while loop. In this do while loop we have these two lines, that is flag I equal to true and turn equal to j. Flag of I equal to true indicates the process Pi is ready to enter the critical section, but turn equal to j indicates presently process Pj is executing in the critical section. So we know that as per the requirement of mutual exclusion, at a time only one process will be allowed to execute its critical section. So as process Pj is presently executing in its critical section, the process Pi will not be allowed to enter its critical section. So that's why here after this we have this while loop, while flag of j and turn equal to j. Means here flag of j means j is ready to execute in its critical section, and turn equal to j means presently j is executing in the critical section. Means now it's j's turn. So until j is finishes the execution, it will be in this do while loop only, and once one of these two condition becomes false, like when flag of j will be false, means it don't want to enter the critical section, or when turn is not equal to j, means it's not j's turn, so this while loop will be terminated. So as a result, here the process Pi will be allowed to enter its critical section, because already you have set the flag of I equal to true to indicate that the process Pi is ready to enter its critical section. So as soon as the one of these two condition becomes false, the Pi will be allowed to enter its critical section. So once it completes its execution in the critical section, so you have to set flag of I equal to false to indicate PI has finished the execution in its critical section, and now PI is not ready to enter its critical section. Okay, so after this you have to execute the remainder section, and this is the end of your program process. So in this way, a solution can be provided for the critical section problem for a process PI using the Peterson solution. Okay, so this that was a software solution. So again, after that there are a number of the hardware solutions, okay, for the critical section problem. So let us discuss those one by one. So it starts with the concept of lock. Means here, whenever a process want to enter its critical section, so it should acquire the lock on that process. Okay, whenever the process gets the lock, then only it will be allowed to enter the critical section. A very simple solution. So it can be implemented in this way. So while true we have, so initially it will try to acquire the lock. Whenever it acquires the lock, the process will execute in critical section. So once it completes the execution of critical section, it will release that lock and it will execute the remainder section. So very simple. Okay, so the one more solution is using the test and set instruction. So many modern computer systems provide a special hardware instruction such as test and set and swap that allows us to either test and modify the content of a word, or to swap the content of the two words atomically. Okay, so here test and set means this is to test and modify the contents of a word. Okay, and here swap means this is to swap the content of the two words. Okay, so by this here the definition of test and set instruction is like this. So the test and set function, it takes only one argument of type boolean star target. So here we have boolean rv equal to star target equal to true, and return rv. Okay, so return rv is nothing but a boolean value. Means here we have a process. So initially we take this target the star target is a target process. Okay, so this process will be this is equal to rv. So after that we make star target equal to true, means we'll allow the process target to start its execution, and after that we'll return the modified value rv, which indicates the process target is allowed for the execute in the critical section. So let us see how the mutual exclusion is implemented via the test and set function. So here by this the process PI will look like this. So we have the do while loop here, so infinite loop. So in that first we have one more while loop here, while test and set of ampersand lock. Okay, so here when the test and set of ampersand lock is true, means if the lock is available with some other process, you cannot enter the critical section. Okay, so that is known. So once the lock is available to you, this condition becomes false. So that's why when this condition is true, you should not the process PI cannot do anything. It will be simply waiting because the lock is not available. Once the lock is set, so okay, so it can enter its critical section. So once it enters the critical section, it will make lock is equal to false. Okay, and after that remainder section is executed. So in this way the mutual exclusion is implemented via test and set, and we know that mutual exclusion means at a time only one process will be allowed to execute. Okay, so here as the other process is acquired lock, the process PI will not execute in this critical section. It will be waiting. Once the block is available, then only it will enter the critical section. So this is with respect to the test and set. So we have one more method, that is swap, which is going to swap the content of two words. So the definition of swap is here. So white swap boolean star a boolean star b. So boolean temp star a, okay, temp equal to star a equal to star b equal to temp. So this is known to you. This is how you can swap the content of these two words a and b. So next we'll see how exactly the mutual exclusion is implemented via the swap instruction. So again we have a do while loop here, and here for the swap we take one more variable, that is key, which is initialized to true. Okay, so here while key is equal to true, when means here when the key value is equal to true, we'll simply call the swap function, swap ampersand lock and key. Okay, so this will be continued until key is equal to true, and key becomes false, then only it will allow to enter the critical section, and once it completes the execution, the lock will be equal to false and the remainder section will be executed. So in this way the mutual exclusion can be implemented using swap. So at last we have a full solution here. So it's an algorithm using test and set and swap instructions that satisfies all the critical section problems. Okay. So here we have used the two variables here. One is boolean waiting of n, another one is boolean lock. So these data structures are initialized to false, means these two. So here do waiting of I equal to true, okay, and key is equal to true. So while waiting of I and key, so key equal to test and set of lock. Means here for process pi, so each time we take process pi. So waiting of process pi is equal to true, means presently pi is waiting for execute in its critical section. So key is equal to true, okay, means the permission can be granted. And after that, while waiting of I and key, when these two are true, we'll try to acquire the lock on for the process pi. Okay, so here we call the function test and set of ampersand lock, and we know that when the lock is not available, it will not return the true value. Okay, so that's why here whenever it the lock is available, okay, so it will return that value to key. Okay, and after that waiting of I will make it false, means it was waiting for entering the critical section. Now to indicate that it has entered the critical section, will make the value of waiting of I equal to false. So after that the process will be allowed to execute in its critical section. Okay, so after that we'll change the value of j equal to I plus 1 mod n. Okay, and after that, while j is not equal to I and the negation of waiting j, so j will be incremented by 1, j equal to j plus 1 mod n. Okay, so after that if j is equal to I, lock will be equal to false, else waiting of j equal to false. Okay, after that again it will execute the remainder section, and at the end we have while true. So this is a do while again infinite loop. So here we know that the mutual exclusion is again implemented, because we know that whenever process pi want to acquire the lock, it will not, because test and set already in previous slide also we have discussed this. Okay, so this will return the value whenever the lock is available, and if the lock is acquired by some other process, it will be simply waiting. Okay, so that's why until this condition is true, so it will not go for here. Okay, so this is how the mutual exclusion is implemented using the test and set. Okay, so with this I stop the discussion today, and the remaining portion we'll discuss in my next video. Thank you.